Good afternoon. My name is Professor Anthony Lupo, and I am with the Atmospheric Science program at the University of Missouri. And I was supposed to be with you today, but unfortunately I cannot be with you in person. But hopefully this recording will be okay, and I will at the end let you know how you can contact me by email. Today I'm going to talk about atmospheric blocking and climate, and we'll talk about the impact of blocking on human health, environment, and agriculture, including a study that we're doing on the impact of or the connection between blocking and drought in agriculturally sensitive regions. Atmospheric blocking is a phenomenon that may occur on a relatively small, large time scale and large spatial scale, and it can dominate a region's weather for an entire season, not just a few days. Okay, and we'll see that when we go forward. All right. Some examples from Turkey's weather were highlighted in publications by Efe et al. In 2019, there was the cold wave of March 1985 and the September heat wave of 2015 that were both the result of unusual blocking in your region, in the Turkish area in Eastern Europe. Blocking in the Northern Hemisphere typically occurs, all right, and between 140 degrees east, which is near Southeast Asia, all the way to 120 west near the coast of the United States. And the peaks are just offshore for Asia and then in the Gulf of Alaska region at 150 west. And in the Atlantic, there's a peak near 0 degrees. All right, and near Western Europe, and then again in Eastern Europe and Western Asia between 50 east and 90 east. All right, and of course, Turkey, the USA is right here where there's a minimum of blocking, and Turkey's at an area where there's a maximum of blocking, which is why there are many studies that come out of ITU on the effect of blocking, including those by Efe et al. That I discussed earlier. But the warm case for blocking was with a blocking event over Northwest Europe, and this led to warm air being carried out of North Africa and into the Anatolia region for a long period of time during that month. And then the cold case was involved with blocking over Eastern Europe and Western Russia. And this allowed for the advection of cold air into the Anatolia region, including some unusual snowfall. So blocking can have a great influence on meteorological conditions, not just in the areas that they occur, but in the upstream and downstream region as well. There really isn't a set definition for blocking or criterion that's commonly applied. And there was an article by Pinheiro et al. That reviewed some of the blocking criterion out there. And this publication came to the conclusion that each different blocking criterion had its pluses and minuses, all right, its positives and negatives, and but they all gave pretty much the same climatology, whether you were using the zonal index method, which our group seems to favor, the thresholding method, or potential vorticity. But a generic definition of blocking is that it's a long-lived mid-latitude, mid-tropospheric, quasi-stationary, positive geopotential height anomaly. And for that reason, blocking tends to be a very dynamic feature that you'll find it in the mid-latitudes, all right? And this is different from a subtropical high pressure, which is generally forced by surface conditions below and as a response to the convection at the ITCZ. Well, blocking is still not a well forecast problem, especially at onset and termination. And the processes that contribute to blocking are somewhat understood, although not fully. And of course, as this presentation will highlight toward the end, is that blocking can be responsible for economic damage in terms of agriculture or capital and infrastructure, and of course societal losses in terms of cost of human life. A lot of times the losses from blocking in terms of human life are more indirect, but they can be direct as well. When we look at the dynamics of blocking, the work that we did earlier, about 30 years ago, demonstrated that all blocking events are accompanied by developing upstream cyclones, which means that the position of the storm track is very important when it comes to whether we'll get blocking and whether it will be supported. Our work was not new in proposing the idea of an upstream cyclone. Our work just showed that every blocking event that we studied was accompanied by these upstream cyclones. And we studied we studied all cases in the Northern Hemisphere over a 3-year period and then beyond. Blocking has been shown to be the result of interactions between these planetary scale waves that occur over the Pacific region, the Atlantic region, and in the continental region, in association with the positions of the continents and the topography, but that you do need those synoptic scale waves in order to get blocking. You need the cooperative interaction of those two things. And of course, in the Northern Hemisphere, some of our work has shown that the interaction between the large and small scale tends to be nonlinear and synergistic. And what we mean by that is mutually beneficial to both scales. In the Southern Hemisphere, the interaction may be as simple as constructive interference, which means that blocking is generally shorter lived in the Southern Hemisphere. All right, and here's an example of those wave-wave interactions from Reynolds et al. In our study of the forecast model's ability to replicate the onset of blocking. So typically you see a low pressure, all right, in the sea level pressure maps, and here's an example from East Asia near Japan and the Sakhalin Islands and the peninsula. We see a small scale or a shortwave trough in the 500 millibar height field. We see a relatively large scale ridge feature and a shortwave ridge feature. And we see a jet streak rounding the base of our trough, which is going to help to develop the mid-latitude cyclone through the influx of positive vorticity or cyclonic vorticity, but it's also going to be involved with an influx of negative or anicyclonic vorticity for the ridging event. And this is just before block onset. And then 24 hours later, we see the cyclone developed fairly rapidly and moved well off to the north. The shortwave ridge and the large scale ridge both interacted, and the shortwave ridge amplified to the point where these two events merged and we have the onset of blocking in the East Pacific. And the jet streak is now rounding the top of the ridge, which is analogous to what happens a lot of times when these jet streaks round the base of a trough. So it's helping the ridge to build up. And here's an example of that same dynamics at work in the 500 millibar maps for a case of blocking that lasted from January 23rd to February 15th in 2014. The reason we look at the 4th through 7th of February is that the onset of blocking is usually accompanied by an intensification of that blocking event. And then as long as no other cyclones interact with the event, the block weakens. But if you get a second cyclone to interact with the blocking event, it can refresh the blocking event and cause it to strengthen again. In the 1980s, work by Colucci and Mullen, they both suggested that as long as cyclone waves were about a quarter wavelength upstream, the blocking events would form in association with these mid-latitude cyclones. But our work further stated that the 1/4 wavelength is necessary, and as long as you had cyclones doing this throughout the block life cycle, you could support it. But if the synoptic scale cyclone was too far upstream, it would be in no position to support the block. If it was closer than this, it would lead to the weakening of blocking. And that gave forecasters something to look for in the 500 millibar height maps and in the surface maps. All right. So this viewpoint on blocking suggests that local forcing is what's necessary. All right. And that blocking events are not necessarily hemispheric in nature. Later on, this hypothesis was supported statistically by Lahanis in Oakland, and they suggested that if blocking were forced hemisphere-wide, there'd be a greater frequency of the simultaneous occurrence of these things. In other words, you'd see 2 or 3 of these more often than you do, and you only see simultaneous blocking about 5 to 25% of the time, more so in recent years because there's been an increase in blocking. And obviously, the more blocking events that we have, the greater the chance there is that you may have 1 or more occurring at the same time. All right. And some of our climatological results also demonstrated that there's a correlation between the strength of the mid-latitude cyclone development and the block intensity and duration. All right. And others made those, since then, others have made that connection as well. And some researchers in Russia were the first to demonstrate that blocking is an important contribution to continental climate regimes. All right. And we use their idea to separate out northern hemisphere blocking as oceanic versus continental. All right. As I've said here before, just a bit ago, there's been a recent increase in the occurrence of blocking. All right. We see this in regional studies like Häkkinen et al., which studied blocking over the Atlantic since the turn of the 20th century all the way up to today. And they showed that blocking was more common in the Atlantic Greenland area in the middle part of the 20th century. And in the late part of the 20th century, the occurrence dropped off, but that we've seen this recent increase in occurrence. And Mokoff et al. Also found similar results, though not as dramatic. And their study goes all the way back into the the late 1800s, where we saw a decrease in blocking in the late 1800s and into the early part of the 20th century. A little bit of an increase in the middle part, and then a more recent increase. And of course, the Mokoff et al. Study looked at 3 different criterion from about 1950 onward. All right, and all 3 criterion are showing similar behavior. Well, why these increases in global blocking or regional blocking? All right. Well, we examined that question in some of our studies, and we looked at variability associated with the Pacific Decadal Oscillation, as well as the North Atlantic Oscillation and the AMO. And what we found is that during the 80s and 90s, or at least from the late 70s to the mid 90s, all right, both the NAO and the PDO was in its positive phase, while the NAO, all right, was more of a negative phase, all right, and we saw a decrease in blocking in the northern hemisphere, all right, during the 70s, late 70s to mid 90s. Blocking picked up again when the PDO switched over to a negative phase, and the NAO also switched phase around that time, and blocking increased. And there's some suggestion in our climatology as you go back toward the middle part of the 20th century. And again, I'd love to extend our study back there and look at studies like, compare to studies like Mokoff and Häkkinen to see if there was a big increase in blocking in the middle of the 20th century. These changes are more pronounced in the Southern Hemisphere, although we're not going to talk too much about the Southern Hemisphere today. You can see the absolute minimum in the blocking during the 80s and 90s, and then an increase around the year 2000 in the Southern Hemisphere. And the 70s and 60s seem to be more active in the Southern Hemisphere. Our group was the first to develop an intensity index for blocking, and it based the strength of the blocking on the mid-latitude height gradients. So you look at the height gradients to the north of the blocking, to the east of the blocking, and the west of the blocking, and take an average of that. And then we go ahead and take divide that value by the central height for that day, subtract 1, and multiply by 100 so that we get a number somewhere between 0 and 10. And then we average the number of days, or we average the BI number over the number of days that the blocking exists, so that you have a blocking strength. In the Northern Hemisphere, we see that since 1968, you get about 31 blocking events per year. The mean duration is 9 days, 9.5 days, and the mean block intensity is 3.13 blocking BI units, and that's a unitless number. The Atlantic region tends to see a large number of events per year, and with a mean duration that's similar to the hemispheric average, but Atlantic region blocking events tend to be stronger. And again, these things tend to occur at the end of the storm tracks in the Atlantic, Western Russia, and in the Pacific. All right, and if you compare where the blocking events have occurred in the late 20th century versus the early 21st century, you see that more blocking events have occurred in the early 21st century, but that their general location has not changed. All right, you may be seeing more blocking in the continental region of Asia, as shown here. And of course, Wiedemann et al. Versus the early 20th century results, which is a publication that I did with Professor Batiar, FA, and some others, showed an increase, strong increase in the number of blockings from the late 20th century to the early 21st, which again, we think is the result of interdecadal variability. The duration is increased, but the intensity has decreased. Okay. And if we look at the same data from a publication by FA et al. About blocking and the effect on Turkey, and look at the late 20th century versus the early 21st century, the FA et al. Study finds consistent increases in the number of blocking and sees similar decreases in the strength of blocking in regions that affect Turkey. And of course, our group has shown that blocking is more frequent in La Nina years in the late 20th century, but that changed in the early 21st century, that you're seeing more blocking in the El Nino years. So if you look at the 50-year study, you see almost no variability due to ENSO, but that the El Nino variability seems to flip in response to changes in the phase of the Pacific decadal oscillation. And that's something we won't get into that too much here. Again, we're here to talk about blocking in general. And of course, an earlier study of ours proposed that blocking characteristics would change in a warmer world. If we do see a strong warming due to climate change, that blocking might become more persistent, all right, and occur more often, but be weaker overall. And that's, of course, consistent with the changes we've seen in the early 21st century. All right. Mokov et al. Looked at Atlantic blocking from the mid-20th century to the early 21st century, and then looked at some model projections out to 2100, and their results suggested the early increase in the 21st century, and then a leveling off of blocking activity out to 2100. And Woolings et al. This was a review paper on blocking that looked at the future projections of blocking from the CMIP models. And these projections showed a stronger jet stream in association with warming. And the CMIP5 models showed almost no change in the frequency of blocking, but found some changes in the future locations. But this review article talked about the future projections and looked at different methods for how you detect blocking, and different methods gave slightly different answers. All right, as one can see in this map. All right, this one looks at blocking in June, July, August, and December, January, and February. All right, using the anomaly method, and they show increases in blocking. This is the zonal index blocking, and that's more consistent with the Mokov results showing slight decreases. And then if you mix them, kind of an overall no change, but some differences as to where they occur. Well, we were going to talk about blocking in association with human health and the environment, because blocking is associated with extreme weather conditions, all right, often. And both in the area where the blocking event is, you're typically very warm and very dry, all right. And then, of course, in the upstream and downstream regions, you can see anomalous cold, and you can see wet conditions as well. All right, so cold waves. Cold waves are definitely something you see in the downstream of blocking, or the upstream of blocking, all right, on the periphery. This is for North America. The Quiros et al. Study looked at North American events. Lupo et al. For Asia. FA et al. Looked at the blocking events in Eastern Europe and Turkey. And then Est et al. Is a study of blocking on cold waves over North America, with a special emphasis on the central United States. And of course, cold can be a killer. All right, cold often kills more people than extreme heat, but cold can also cause lots of accidents due to increase in snow, cause a lot of hardship in terms of heating, all right, or lack of heating if somebody doesn't have the ability to heat their home. All right, and we kind of looked at this, we kind of looked at a case during the winter of 2019, from February 1st to March 10th. All right, and the first part of February was unusual in that there was no blocking in the northern hemisphere. All right, and that had a particular impact on our weather in the central United States. And we looked at the effect of blocking, but we also looked at the impact of northern hemisphere regime transitions from amplified flow to zonal flow, all right, or changes in the Arctic oscillation. All right, so from February 1st through the 10th of February, Missouri and the central United States were underneath weak ridging conditions, and you can see this at 500 millibars as well as 850 millibars. Then from February 11th to February 20th, you had some weak blocking in the Pacific region. There was also weak blocking in Western Europe, and you can see much colder conditions dominate Missouri over those next 10 days. And then even colder yet from about February 20th, all right, to March 10th, we had blocking. We had a very powerful blocking in the Alaska region and over Northwest Europe. And in fact, these two blocking events together were the 10th strongest in the 50-year record that we have on blocking, the 10th strongest combination of blocks for the two ocean basins, and that generated a lot of cold weather for us, as we'll see here. All right, from the 1st to the 10th of February, temperatures were above normal for the Missouri region and the states bordering that. So as we saw temperature anomalies as much as 4 Celsius in the southern part, and the area was generally dry. When the weak blocking occurred between 11th of February to 19th of February, temperature anomalies were colder, and we had wet and snowy conditions. And then between February and March, this strong double blocking event, all right, in the Atlantic and Pacific, the 10th strongest event in 50 years. Temperature anomalies were way below normal at this point, with precipitation, and more of that precipitation showing up as snow. Heat waves and drought, they can also be a problem for human health. Many people died in some recent heat waves in Europe and Russia. All right, and we've got some examples of that. Western North America also saw a lot of increased fatalities in June and July of 2021, believe it or not, due again to the unusual occurrence of blocking. And this is a map from July 2010 for the Northern Hemisphere, showing the heat in Western Russia. Then you had cool and flooding upstream in Central Europe and downstream over Pakistan, which both of these events caused some fatalities as well as a lot of damage. And you had heat in far eastern Russia as well. So these excessive heat killed a lot of people, because especially in Russia, where during 2010, where the overnight lows were very high, much higher than they're used to. And since people don't have a lot of air conditioning, again, it caused a lot of fatalities. All right. Excessive heat is also responsible for a lot of environmental damage. And we saw this at the 2010 events over Western Russia and Eastern Russia in terms of very dry conditions, a lot of forest fires. And because blocking is high pressure areas, a lot of that forest fire smoke is captured in the blocking events, which does a lot of damage to the forest areas, but also to human health in cities. And in Russia, there was the problem of peat bogs that burned. And then this is a figure showing blocking that persisted for much of August 2004 over Alaska in the United States. And this persistent blocking throughout the entire month, all right, beginning of August, middle of August, end of August, the persistence of blocking through the entire month destroyed forests. A lot of forest fires led to a lot of record highs in that area. Fortunately, this area is not very populated, but people in that region called August 2004 baked Alaska. All right, baked Alaska. Blocking can also cause some very odd conditions, like mini holes in the ozone layer. If you get particularly strong blocking, especially in the Northern Hemisphere, a paper by Sitnoff et al., all right, shows that the ozone concentration goes way down in association with blocking. And here's the middle of May 2010 and early August 2010. Again, some very powerful blocking events associated with that Russian drought. And these middle figures show the anomalously low column ozone over northern Russia and Scandinavia, and even stretching into Anatolia during August 2010. So even areas near in Turkey and especially eastern Turkey saw reduction of this column ozone. And there was also a strong increase in the total column water vapor. And it's this humidity which helps to lead to a increase in the number of human fatalities. Of course, hot, humid weather doesn't give the body enough time to relieve itself through sweating, and or it doesn't give you enough opportunity to relieve the overheating through sweating. So a lot of increased humidity as well. And this had a huge impact on human health. Air pollution and blocking have long been connected. We know that the strong stability in the lower troposphere is going to provide the conditions favorable to capturing air pollution, such as low wind speeds, very little change in the upper air temperatures, very little change in the ridging. And since the ridging is moving slowly, the persistence of these conditions for many days. And actually, the ITU faculty, including Dr. Ali Deniz and many others, have published some studies detailing the role of blocking in air pollution events for the country of Turkey. And they've also looked at other types of events that require stable environments, like persistent fogs. And persistent fogs can be dangerous for aircraft and for marine travel. So faculty at ITU have been, we're at the leading edge of studying some of these effects on human health and environments. Agriculture and blocking. Blocking is often, again, associated with heat waves and drought. And in the drought portion is what's bad for agriculture. And of course, we have two models of how blocking can influence agriculture in the area. And one is what I'll call the Eastern Europe model and Western Russia versus the Central USA model. And why do I say there's two models? Well, the Eastern Europe model involves teleconnections and an increase in blocking over Eastern Europe and Western Russia, as we're going to see. The Central USA problem is caused by the lack of blocking upstream in the Pacific. So two different models on how blocking contributes, or the lack of blocking contributes to drought conditions. Eastern Europe and Western Russia. All right, so I did a study with colleagues from Ukraine and Russia, and we studied the agricultural conditions in this region over the from the mid-20th century to the early 21st century. And we found that the negative Eurasian pattern, all right, an enhanced Rossby wave pattern over Europe and Asia, was associated with anomalously dry years. All right, so we actually found about a dozen drought years. All right, strong anomalous high pressure at 500 millibars. Whereas in wet years, you tend to have a positive Eurasian pattern and wetter conditions or cooler conditions over this region, troughing. All right, so that kind of makes sense. But when we look at Eastern Europe and Western Russia, the dry versus wet years, the teleconnections flip sign, as we showed on the previous page, you get a similar number of blocking events in wet versus dry years, believe it or not. But you get more blocking days in the dry years, and the blocking events are stronger in the dry years. All right, so there is a difference in how blocking occurs within this region. All right, similar number of events, but more persistent days that are blocking days and stronger. Right. And in the summer of 2022, we saw drought conditions over Eastern Europe and Western Russia, and this is about to become the subject of a case study for a student of mine. We can see the precipitation anomaly, again, very dry conditions over Western Europe, Eastern Europe and Asia. All right, and that's accompanied by increased evaporation over those same regions. All right, Turkey has been anomalously dry this summer. Eastern Turkey is included in this drought region. Western Turkey seems to have fared much better, but Eastern Turkey is also associated with this drought. And of course, this year there were 4 very strong blocking events during the summer months. All right, the summer months from 1 June to 31 August, and almost half the summer was blocking days. And these events were quite strong. All right, so half the summer, strong blocking events, negative Arctic oscillation, and also a negative NAO and PNA early in the summer. Now, this point here is significant, negative NAO and negative PNA, because usually these two teleconnections anti-correlate. But during this drought year, they tend to correlate. And so we're going to investigate that point further. In Central North America, drought is associated with, all right, a negative PNA pattern, and the central USA is the region inside this box, including Missouri. Now, over North America, we always have a ridge every summer, and it depends on where that ridge is, all right? In very dry summers, we have ridging over the central USA. In very wet summers, we have ridging over the western USA and eastern Pacific, and troughing over the central USA. All right, so it's a matter of where that ridge sets up as to whether we get drought or not. So the teleconnection activity, lack of, or it's a PNA is negative, and the PNA is positive in wet years. So negative in dry, positive in wet. The thing that characterizes North American droughts is the distinct lack of blocking upstream of North America in dry years. All right, so if we go back to the map, you tend to get much more blocking in this part of the world, which helps to force wetter conditions in the middle of the country. All right. The lack of blocking in this region forces ridging over the central USA. All right. And that's a distinct feature of almost all of, and well, I shouldn't say almost, it's a distinct feature of all of our droughts. All right. The 2012 drought, there were 0 blocking events all summer in the Pacific. But in the summer of 2022, which has been a severe drought, we've seen again the lack of precipitation with a bullseye over Missouri, the lack of, or a strong evaporation anomaly, again, a bullseye over Missouri. And so we're experiencing the worst of the drought conditions. And in this summer, there was only 1 very weak blocking in the Pacific. All right, when normally we expect 3. All right, so normally we expect 3 blockings in the Pacific. And in drought summers, you'll get 1 event maybe. All right. And of course, in Central North America, we had a case back in 2005 where June and July were very dry. And then during the middle of August, we had blocking for 2 weeks in Alaska, and that drove the storm track over the central USA. And we had over 30 centimeters of precipitation in 2 weeks. So we went from a summer that had almost no precipitation to a summer that looks more normal. And we got almost all the precipitation in 2 weeks. So in conclusion, there's been a significant increase in northern hemisphere blocking occurrence, as we've shown. They've become more persistent, but a little weaker. But models are suggesting that blocking occurrence will level out and we won't see much change in the occurrence of blocking. And that blocking can have an impact on human health. All right, we see that, all right, in areas that they occur, but upstream and downstream as well. All right, and I've highlighted some studies that showed that. But the final point is that drought, which is important for agriculture, is driven by the occurrence of blocking over a region, or in some regions like the central USA, the lack of blocking upstream. Okay, if you have, I'm sorry if I've gone a little long, but thank you for your attention to this seminar. And if you have any questions or comments or criticisms, please send them to me. This is my email on the screen below, lupoa@missouri.edu. And please reach out to me if you do have questions or comments. I would be very happy to hear from you and to hear that you had some interest or some desire to share your thoughts about this presentation. So again, thank you for the invitation. And I was glad to give you this presentation today.